Hi, everyone. My name is Song Michael Shea. I'm a PhD student at Stanford. I'll be talking about my project, our project about optimizing the data mixtures for pre-training language models more efficiently. It's called Do-Re-Mi. This is joint work between Google and Stanford, with a lot of great collaborators, including Percy there and also Hugh in the audience. Okay, so the first thing, I guess for context, is just that the language model data sets are growing very fast. So this is just a plot of the size of the data sets over time. The y-axis is the log of the number of tokens in the data set. So the plot is roughly linear. You can see that the size of the data sets are growing roughly exponentially. And if we just zoom into one of the models here, Palm, which is sort of outdated, Palm is a 540 billion parameter model. It's trained on about 800 billion tokens on 6,000 TPUs for 2 months. Just as a rough estimate, it costs Google about $10 million in terms of GCP opportunity cost. They could have been serving it to customers. So what we're really focused on here is that it's trained on a huge data set and it's getting bigger. And the huge data set is what I see is big knob that we can turn with a huge potential for improvement. So the question is, can we improve this data for better training efficiency and performance of these models, which costs a lot to train? And the first thing to note is that the choice of this training data is actually very crucial for these language models. So even heuristic filtering methods can significantly improve the downstream performance. So one heuristic method is to train a binary classifier that assesses the similarity to Wikipedia and books as a proxy for high quality text. And if you do that, the green line here is the downstream performance after filtering, and it just this heuristic filtering can have a significant impact, improving the downstream performance of these models. But these methods are largely heuristic. Our goal is to develop more principled and scalable data-centric methods for improving language models. The particular setting of this paper is in data mixtures. So language models data sets typically come from a number of domains. A domain here, we're talking about data sources like Wikipedia, web crawls, or books. And the question is, for a fixed training budget, can we decide how much of each domain should we sample to train on and put in our data set? And really the question here is, what's the target for data selection? If we had a target data set, some examples of what we want, we could use that and a large raw data set that we're selecting data from and do a number of things. You could do importance resampling, you could train a binary classifier, you could do retrieval. But in any case, you use these two pieces of data to train something, and then you can use that to select a subset of what you want. And this is because you already have the target. But often there's no clear target. So these language models are very multi-purpose, and you don't know exactly what they're going to be used for down the line. So how do we select data for this? Previous approaches for data mixtures include manual tuning or setting these data mixtures by intuition, for example, in the pile. Another is tuning for downstream tasks. So you gather some representative set of downstream tasks, and then you might use some kind of expensive heuristics or RL or search. The reason it's expensive is because pre-training is now in the inner loop. Whenever you test a new set of weights, you need to pre-train and then see what the effect was. You might end up training hundreds or maybe thousands of models here. So instead, what we do is we formalize this as robust optimization. So the idea is that we don't know the target, so we want to be instead robust to the unknown target. And the goal is to do well on all of them, try to do well on all the domains simultaneously. And the optimization problem that we try to solve is this. We're minimizing over the model parameters on the outside, and the inner on the inner part of the objective, we have a maximization over the domain weights. And the domain weights weight the loss on each domain. But there's an issue with this optimization objective, which is that it could be very pessimistic. So if one domain is very noisy, the losses on that domain are high, we might end up just putting all the weight on that domain. To get around this, we instead optimize for excess loss, which is the loss gap between the model we're training with parameters data and a pre-trained reference model. And that gives you a baseline for how well you can expect to do. So the loss that we're optimizing in the min-max objective in the previous slide is actually a difference between two losses. And just to get an intuitive picture, so when excess loss is low, for example, that means the gap is small, and perhaps this example has already been learned, or maybe this example is actually very noisy or not learnable. The reference loss is large, and it doesn't take much to meet it. When the excess loss is high, however, that means that you have a large gap. There's a large room to improve. Because the reference model is sort of a certificate that you can reach such a loss on that example. So basically, excess loss levels the playing field and helps to reduce the pessimism and sort of naturally downweights some of this noisy or unlearnable data, as well as some of the easiest data. And the next question is, how do we do this robust optimization over the domain weights? So we do, basically we do this loop, which is technically alternating online mirror descent. We alternatingly update the domain weights alpha, where we upweight the domains with highest excess loss. And then we do an update on the model theta, where we reduce loss more on the upweighted domains as a result. And then as an output, we output the average domain weights over the time steps. So if you put all of this together, we're essentially dynamically adjusting the domain weights during training and then aggregating this over time. If you put all of these ingredients together, we get the algorithm called Doremi, domain reweighting with minimax optimization. Where in the first step, we take in some reference domain weights. It's just something to start off with. It could be uniform domain weights. It could be the natural weights that come from the sizes of each domain. You use this in the first step to train a small reference model. The reference model is used in the calculation of the excess loss in step 2, where we train a small proxy model with distributionally robust optimization. And the output of this step is that we get some optimized domain weights. And these domain weights define a reweighted data set. This reweighted data set we can use to train a much larger language model. And I guess the punchline here is that the Doremi data mixtures that we find can actually speed up the large language model's pre-training by 2.6 times on 8 billion parameter models. So just to go into that a little bit more, we tested out training some 8 billion parameter models on the pile. So the blue line is the 8 billion parameter models that were trained on the weights found by Doremi. And it achieves the baseline's average downstream accuracy about 2.6 times faster. And eventually, if you give it the same training budget, it gets to 6.5% better average performance. One thing to note is that the size of the small proxy model we use here is 30 times smaller than the 8 billion parameter model, so 280 million parameters. And optimizing those domain weights using that small model only takes about 8% of the total training compute of the 8 billion parameter model. And we also tested this across many model scales. So, and we find that it consistently improves language model training across different model scales and doesn't diminish across scales. And so we think that it has a hope of scaling up to much larger models as well. Another interesting thing is that we find that even though Doremi reweights and so necessarily has to downweight some domains, the perplexity on all the domains seems to improve. And this, we conjecture, is due to some sort of positive transfer across the domains. If you inspect the domain weights, Doremi tends to upweight some of the more diverse web data domains. And another interesting tidbit is that even though Doremi downweights Wikipedia a little bit, the accuracy on Wikipedia-based tasks like trivia QA actually increases. And perhaps the sort of most exciting part of this is that we can iterate the process. If you draw an arrow back from the optimized domain weights back to the reference weights, you can use the optimized weights to train a new reference model, which is better, and then you get out better optimized domain weights if you do step 2 again. And we did this on the GLAM dataset, which is one of the datasets used in Palm, where we have access to some Oracle domain weights that are tuned on downstream tasks. And if we start the iterated Doremi process starting from uniform reference weights, iterated Doremi converges in 3 rounds, and it finds these weights naturally that are pretty similar to the downstream tuned weights. And indeed, the second round of Doremi matches the performance of these Oracle domain weights that were tuned on the evaluation tasks themselves. Okay, so to wrap up as a summary, so without a target for data selection, our idea is to be robust to the target. And Doremi does this using robust optimization. It optimizes the data mixture at a small scale and transfers that to a large scale to speed up LLM pre-training. Cool. Thanks. Happy to answer questions.
One quick question. Okay, quick, make it quick. Thank you.
I wonder how this compares with just use the reward model to filter your pre-training data.
So I think the most the closest comparison there is the sort of heuristic filtering method. One thing is how to train the reward model. I guess reward models are usually trained by you gather some kind of human preference data. So on the pre-training side, this is usually done by the sort of proxy for high quality text is Wikipedia and books. You train this very simple classifier because you need to process a lot of data, and we do see performance gains from that. And this is actually on top of that filtering. So the PAL has already been filtered, and if you reweight the domains, we can get a further improvement. Sorry.
What model?
They use like it's like a bag of hashed n-grams classifier from fast text. It's something. It's not a neural network.
Thank you.
Yeah.
Thank you, Sang. Great topic. Do we have? Do we have speaker for the next presentation? Ali? Yes. The topic is what makes ImageNet look unlike Leon? Can we get the slides up, please? Okay, just a second.
1, 2, 3.
There you go.
Is this working?
Yes.
Okay, hi everyone. I'm Ali, and I'm going to talk about our work, what makes ImageNet look unlike Lion. This is a joint work with my advisor, Maurice Hart. Let's get started. Is this working? Okay. I'm sure many of you have worked with ImageNet, you know, the workhorse of computer vision for nearly a decade. It contributed some curated images for supervised learning at the time, but the field has seen this new dataset, Lion, kind of taking the field by storm. And you know, Lion is just a bunch of image text pairs with minimal curation. So I think an interesting question is, what makes Lion actually different from ImageNet? And you know, when I say that, I'm not talking about the scale. Of course, Lion is just massive scale. And I'm also not talking about the language supervision. I'm exactly talking about the same task, maybe image classification. And I want to see what Lion may be able to offer, which ImageNet was not able. Okay, so what can we do? We can create a new data set, which I'm going to call it LionNet, which basically queries Lion images instead of what ImageNet has done. And we're going to create a new data set in the format of ImageNet with the same structure, but just with Lion images. How can we do that? You know, Lion at the outset is it's just much like a text-based search engine. So for every class in the ImageNet, we can design a query, a textual representation, and that can be a description of the class. And then we can go over Lion captions and see which of them are really similar to our query. And this way, we can query Lion. Also, I'm sorry I guess my PowerPoint was in PowerPoint, but this is Keynote, I guess. So if you see some things that are messed up. Okay, we can create a data set named Lion. Why do we need this? I'm going to compare it to ImageNet. And I think we are going to learn something about both ImageNet and Lion. And that's interesting because I guess we are also going to, this is also going to have some, you know, some prescriptive value for future data set generation. Okay, before, you know, I'm gonna compare these two, but I'm gonna give you some insight that why LionNet is interesting. So let's think about the generative process where for every class, for every category, generates an image. And in fact, if you're talking about image and text, you can think about the generative process that generates text and image. And when we are generating a new data set for image classification, maybe we would like to sample from this distribution. We would like to sample X given a certain Y. But you know, unless we have access to this generative distribution, we cannot really do this. What we can do is to come up with some selection algorithm, which can rely on both text and image. And what I'm going to convince you today is that sometimes it is really helpful to avoid using the main modality, the image, in your selection algorithm because it's going to bias your distribution. Just avoid it as much as possible. And I'm going to give you a very simple intuition why this is interesting, actually. You know, this is how we create LionNet. We will only rely on text. We have advanced tools from natural language processing which can ensure that that the caption is describing the right topic. And why is this interesting? Assume that we have a selection algorithm which is really precise, so we can be sure whatever we selected is from the right class. What can go wrong if we select the images from the image content itself? In fact, just look at ImageNet. For example, during human annotation, what we might observe is that humans just have some biases. Some images are just easier to be classified. Some images are just more beautiful. Or whenever we are creating a candidate set with image-based search, it's really possible that the search engine is using some visual features. So that's something that might go wrong. There might be a leak of information from the image to our selection. This is something we don't like. And I'm going to argue this is not going to be a serious thing when we use text-based selection. Why? Because condition on the class, the image is just a richer modality. It's just unlikely for the text to have that amount of information. So intuitively, when we select based on this text, there will be some sort of information bottleneck that's going to help us avoid the selection bias that otherwise would be there. That's the whole idea. If you take this home, and that's the right takeaway. So let me dive into how we created LionNet. The only reason we created LionNet is to compare it actually to, to ImageNet. It's not a training data set. So ImageNet, I mean the famous 2012 version, has 1,000 classes, also known as scene sets in WordNet, and at the high level, the way the way ImageNet is created is by querying some image search engine, creating some candidate images, and then human filtering. What we do with LionNet is kind of similar thing. We have a synonym in the scene set, and then we go to the Lion. Lion has some pairs of image and text, and then we do some filtering. We make sure these are just some criteria to ensure that we are choosing the right images. We make sure the synonym name is reflected in the caption. Use whatever text encoder you have. We use some MPNet, fine-tuned by Hugging Face community. Use whatever language processing tool you want to ensure that the synonym and its definition are described correctly by the caption. And then we also did some additional measures and safety measures just to ensure that we are choosing the right images. And these are all very conservative criteria. This is how LionNet is created. I'm sorry that this is not plotted correctly, apparently. So what you were supposed to see here was the wide range of relative frequency. Different classes are reflected with different frequency in the LionNet because they're just more frequent on the web. And of course, LionNet cannot cover all the 1,000 classes because not everything is in the Lion. So what do we observe? Are LionNet images really harder to classify? I would argue no. And we have some analysis on that, but very simple observation is that if you evaluate clip zero-shot accuracy, you see that, in fact, LionNet is just easier for the clip, at least to classify. But do ImageNet classifiers generalize to Lion? I'm gonna say no. And we tested a bunch of models. Some of them are pre-trained on the larger ImageNet, some no. And we see consistent 10 to 15% lower accuracy. That's surprising and concerning. So what can explain that, actually? Let me show you two examples from LionNet. This is the class torch. The top row is LionNet. And you see whenever we have a graphical depiction, which is absent from ImageNet, actually, ImageNet models struggle to classify. And this is pillow. Whenever I have pillow in a kind of unexpected shape, ImageNet models struggle. So why is it the case? Why accuracy is down on LionNet? We claim this is because of the diversity of the images in the LionNet, and we formalize that measuring some sort of intra-class similarity of the images, which is the average pairwise similarity of their clip image embeddings. That's very intuitive way to measure diversity. And we actually show, okay, none of the figures are appearing here. I'm actually arguing that LionNet images okay, you have to assume that, sorry. LionNet images has lower intra-class similarity, and in fact, LionNet is just more diverse. So I guess I talked about this causal graph. There's a theory that can explain why we are sampling from the right distribution. I assume that we have some sort of really strict selection area. Whenever we selected something, it's going to be from the right class. And I'm doing text-based selection. And that's my point about information bottleneck. When we have information bottleneck, we kind of can assume that the image, given the category, is kind of independent from the text. And in fact, we show some weaker independencies enough to get this nice distribution, the desired distribution as the output. I'm not going to explain it. But that's the whole point. I mean, what we don't know here is that I'm actually claiming that this link from the image to selection is strongly present in the ImageNet, which is not present in the Lion, and that's why it's driving the effect. And we did at this point, we are done with the LionNet. LionNet gave us some hypotheses. about the difference, we did 3 different experiments to show that this link, this mechanism, image to selection mechanism, exists in the ImageNet, that it is strong. And just to explain it in 1 minute, if we weaken this link, I'm sorry for this figure. If we weaken this link, what we are going to observe is that ImageNet just becomes LionNet. Of course, we cannot do it with ImageNet, but thanks to ImageNet v2, we already have 3 different versions of ImageNet. They differ in mTOR selection frequency, and we observe that, okay, we have a figure here. And we observe whenever mTOR selection frequency is low, the version of ImageNet v2 just becomes very similar to the LionNet we have. So that kind of says why LionNet is more diverse. It's all about maybe human annotation, it's all about human biases, and it's all about that link. And we also do some other experiments, like we have ImageNet text recovered actually from Flickr. We have ImageNet captions dataset recently recovered about 1/3 of the ImageNet captions. And if you really believe that ImageNet images are selected based on their text, we should observe that. We can look at the text and see if the images are really selected based on the text. And we do not observe that actually. Okay, I'm going to skip this. And also, if you really think that ImageNet images are selected based on the text, you can do a simple experiment. You can look into the Lion captions and find very, very similar captions to the ImageNet captions and create a new data set, which I'm going to tell that's going to look very dissimilar to the original ImageNet. Okay, let me wrap up here. So LionNet enabled us to retrospectively look at ImageNet and see what might have gone wrong with ImageNet. And as you just saw, the new data set, this LionNet, looks very different than the original ImageNet. And we kind of try to explain that in terms of data generating processes. And we think, and as the experiments show, the image to selection mechanism was significantly at play when ImageNet was created. So we think that that's nice to have information bottleneck whenever you're creating a new data set. That's going to help. That's going to avoid any distortion you might otherwise observe from some selection bias. And my last point is that there is a previous work which already shows, that's very important actually, that already shows the robustness we observe from models like CLIP trained on noisy image text data is not about the massive scale of the data. It's not about the, it's not about the language supervision. It's actually about the distribution of the images. And I think our work kind of demystified that aspect. What's that diversity and why it matters? Again, I'm sorry for the slides. It was not supposed to be like that. And thank you.
Thank you, Ali. We are eating into the lunchtime, pun intended. So we'll take only one question, and then I have a few announcements. Quick question?
It's lunchtime.
Yeah, it's lunchtime. All right. So if no questions, then we can pause here. Thank you again, Ali. And sorry for the technical glitch.